Alright, so let us continue with our study of irreducible subsets of affine space. So we have just seen in the last lecture that the condition that the zero locus of an ideal is irreducible is that the radical of the ideal is a prime ideal, okay. And so let's look at some examples, in fact also examples of the zariski topology, how it looks like. So in fact the zariski topology is very special when you take A1, namely the affine line, which is K itself endowed with the zariski topology, okay. So let me make a few statements. So consider, so let's look at some examples. These are general examples about also about the zariski topology and also about irreducibility. So you first consider A1. This is just K with the zariski topology. Okay. Now so what's the zero set of A1? What's a closed subset of A1? A closed subset of A1 is Z of S, where S inside K of x1 is a subset. Okay, this is the definition of a closed subset. Okay, so S is a bunch of polynomials in one variable. Okay, and of course, you know, if you want this closed subset to be non-empty, you should assume that the ideal generated by S is not the whole ring. Z of S is non-empty if and only if the ideal generated by S is not the whole polynomial ring. Okay, this is essentially one of the versions of the Nullstellensatz. Okay, a rather weak form of the Nullstellensatz, which says that, you know, the zero set of an ideal is non-empty if the ideal is a proper ideal. Okay, and so in other words, the elements of S do not generate a unit. Okay, and in fact, you see, what are the irreducible closed subsets of A1? The irreducible closed subsets of A1 are going to correspond to prime ideals in Kx1. Okay, and so the irreducible closed subsets of A1 correspond to are of the form Z of P, where P inside Kx1 is a prime ideal. Okay, but then if K is a field, then the polynomial ring in one variable over the field is a PID. It's a principal ideal domain. That is, every ideal is generated by a single element, and you also know that in a PID every non-zero prime ideal is also maximal. Okay, so the only chances for P are either that it is the 0 prime ideal, okay, and the other chance is that it is a maximal ideal. Okay, so P is either 0 or a maximal ideal. Okay, this means that the 0 set of P is correspondingly A1, because if you take 0 set of 0, okay, the set of all points which at which the function 0 vanishes, then you will get all the points. So when P is 0, you get A1 or a single point lambda belonging to K. Okay. Because the maximal ideal will look like x1 minus lambda. Okay, so if P is 0, then the 0 of P will be A1. It will include all the points. That in particular tells you that A1 is irreducible. Okay, if you use the fact that the 0 set of a prime ideal is irreducible, and if P is a prime ideal which is not 0, then it has to be a maximal ideal, and a maximal ideal is of the form x1 minus lambda for some lambda in K. I told you this is also another version of the Nullstellensatz, but actually in this case, because it is just in one variable, you don't need the Nullstellensatz. Okay, you just have to use the fact that K is algebraically closed. So the fact is that if you take any ideal, okay, which is a proper ideal, then you see, because it's a principal ideal domain, this ideal will be generated by a single element, and therefore the 0 set of this ideal will be just the 0 set of a single polynomial. Okay, so and then the 0 set of a single polynomial will be just the union of the 0 sets of the linear factors of the single polynomial. Any single polynomial can be broken down into a product of linear factors because K is algebraically closed, and each linear factor will correspond to a point. So what you will get is that the only closed sets are just finite subsets of points. Okay, so that means the open sets are just complements of finitely many points, and from this you can see that you take any two open sets, they will certainly intersect, which is what you should expect, because any two of course I mean any two non-empty open sets, because you already know that A1 is irreducible, so any two non-empty open sets have to intersect, but the fact is any two non-empty open sets are just complements of finitely many points, but there are infinitely many points. The reason that there are infinitely many points is because an algebraically closed field is always infinite. A finite field cannot be algebraically closed. Okay, so let me write all that down. Since K of x1, so let me write here it is for P is equal to ideal generated by x1 minus lambda. Okay. Since K of x1 is a PID, principal ideal domain, any ideal is generated by a single element, any ideal is generated by a single element. So Z of S is just Z of ideal generated by S is just Z of F for some element F in the polynomial ring. Okay, but since K is algebraically closed, F can be written as a product of linear factors. The number of factors will be equal to the degree of F. Of course, I am assuming that F is not the constant polynomial. It is not a constant polynomial, because if F is, of course, if F is a constant polynomial 0, then you will get the whole space. If F is a non-zero constant, then the ideal generated by F will be the unit ideal, it will be the whole ring, and the 0 set will be empty. Okay, and the empty set is always a closed set by definition. Okay, so since K is algebraically closed, the F is some ideal generated by F is just ideal generated by x1 minus lambda 1 times x2 minus x1 minus lambda 2 times x1 minus lambda m. Okay, and which implies that the 0 set of S, which is the 0 set of F, is just the union of all these points lambda 1 etc. up to lambda m. Of course, I am putting the set theoretic notation. Some of the lambdas could be repeated, they would be multiple zeros of the polynomial, but the fact is therefore that any closed set is just a finite subset. Okay, and you know what this will tell you is that, see, this will tell you that you don't, at least as far as A1 is concerned, you really don't need to use the Nullstellan sets to get all these results. Okay, you don't need to use the Nullstellan sets. So because a Nullstellan sets is kind of is redundant, it's superfluous in the case when n is equal to 1. Okay, when n equal to 1, Nullstellan sets is just the definition of what an algebraically closed field is. Okay, so you really don't need the Nullstellan sets. So all this can be directly seen the moment you define zariski topology, even without using Nullstellan sets. Okay, so in particular, for example, how do you see that A1 is irreducible? One way is, of course, from the general theory you can say A1 is irreducible because the 0 set, because ideal, it is the ideal of A1 is 0. Okay, and 0 is a prime ideal, therefore the 0 set of the 0 ideal is irreducible, namely A1 is irreducible. That's one hi-fi way of seeing it. But more easier way of seeing it is that, you see, if A1 were reducible, then you should be able to write it as a union of two closed sets, two proper closed sets. But you see, any closed set is finite. So if you are able to write it as a union of two proper closed sets, that means you are saying A1 is finite, but A1 as a set is just the field. So saying that A1 is reducible is the same as saying that the field has finitely many elements, but that is not possible for an algebraically closed field. An algebraically closed field is infinite. Therefore the fact that an algebraically closed field is infinite will automatically tell you in this case that A1 is irreducible. Okay, so note that note that since an algebraically closed field is infinite, A1 has to be irreducible. Okay, so in this case everything is very easy to see just because of the fact that every ideal is just generated by a single element because it is a principal ideal domain. Okay. And I want you to really think, you see, let us put for k complex numbers, okay, put for k complex numbers and take complex numbers a usual topology. Okay. Complex numbers is just the R2, the xy plane if you want. Okay. If you can also think of it as the Argand plane. Okay. The point is, if you think of R2 in the usual topology, see there are so many closed sets. Okay. There are so many closed sets. For example, you take a disk and then you take its closure, that is a closed set. You take a rectangle and take the closure, that is a closed set. You get all kinds of closed sets. But you take C with the Zariski topology, then the closed sets are only finitely many points. You see there is so the open sets are complements of just finitely many points. It is just the open sets in the Zariski topology for complex numbers is just the plane punctured at finitely many points, the huge open sets, okay, and the closed sets are just finitely many points. So you see there is such a huge difference between the ordinary topology and the Zariski topology, and you can from this also see that the Zariski topology is highly non-Hausdorff, okay, because Hausdorffness is a condition that given any 2 points I can find open sets which contain these 2 points and which are disjoint from each other. Okay. I can do that in the usual topology. You give me 2 distinct points on the complex plane, then I can find 2 small enough open disks surrounding those 2 points which will separate these 2 points. The 2 open disks will not intersect, but if you try to do that in the Zariski topology you will not be successful. Okay. That is because any 2 non-empty open sets will intersect, so you cannot find 2 disjoint non-empty open sets containing 2 distinct given points. So you see the Zariski topology is highly non-Hausdorff, and this leads to thinking in a philosophical kind of way. You see the topological spaces which are not Hausdorff are not well behaved, okay, because the Hausdorffness is if you look at it from the topological point of view, it is the fact that it's the uniqueness of limits. Okay. See, in topology the existence of limits and the uniqueness of limits put together is what is called as completeness. Okay. The completeness is the property that limits exist. Okay. For example, when you take subspaces of the Euclidean space, completeness is just the fact that you take any Cauchy sequence in that subspace, its limit should also belong to the subspace. So and of course the limit of a sequence is unique, so you get the existence not only of the unique of the limit but also that the limit is unique. Okay. But the truth is that the uniqueness of the limit alone, if you take it out as a property and forget the existence of the limit, it is this uniqueness of the limit that is promised by a Hausdorff space. Okay. Now so the fact that the complex plane with the Zariski topology being non-Hausdorff gives you the feeling that it's somehow there is no uniqueness of limits if they exist. Now the answer to that is that you shouldn't think that way. In algebraic geometry the notion of uniqueness of limit is not Hausdorffness, it is another property, and that property which is the analog of Hausdorffness is called separatedness. Okay. And so the nice thing is, though the complex plane is not Hausdorff, it is what is called separated. Okay. So, and separatedness is the right analog of Hausdorffness in the in the Zariski topology. So what you should understand is that though at the outset it looks non-Hausdorff, but for all practical purposes there is the analogous property of separatedness, which I will explain later. Okay. Yeah. So fine. So so the next thing that I should look at is yeah, and in fact let me also remind you of a fact from field theory. If you have a finite field, okay, then the algebraic closure of the finite field is countably infinite, okay. This is one fact, so it is infinite. And if you in general if you have any field, then the algebraic closure if the algebraic closure will have the same cardinality as that of the original field if it is infinite, okay. Then the algebraic closure of the field will have the same cardinality as the field itself, okay. This is a fact. It's just a counting argument because you get the algebraic closure by putting in zeros of all polynomials in the field. After all, you go to the algebraic closure of a field because you want to solve all equations, you want to get zeros of all polynomials with coefficients in that field. And but then the polynomials, when you look at zeros of polynomials, the polynomials can be counted by degree, okay. So you can see that somehow you will get a countable union of subsets which are just as the same cardinality of the field, and then you will see that you will again get the union will again be the same cardinality as that of the field, okay. So this is a fact that you can look up from any standard algebra book, okay. So so let me repeat, if the field is finite, then its algebraic closure will be infinite and countable. If the field is infinite, then its algebraic closure will be infinite and have the same cardinality as that of the original field. And why I am saying this is also since I brought in the idea of algebraic closure, I should tell you why this is important. This is important because you see we somehow in this course we are only worried about algebraically closed fields, but you can write equations over fields which are not algebraically closed, okay. For example, real numbers. Then what is the theory? The theory is that first of all whatever equations you write you can always go to the algebraic closure of that field and work there, and for this you need the existence of an algebraic closure, and this is a theorem in algebra from field theory which says that given any field you can find an extension field, a larger field, which is algebraically closed and which is algebraic over the given field, namely that it is gotten from the given field by just adjoining roots of polynomials with coefficients in the given field, okay. So this existence of algebraic closure tells you that no matter what bunch of equations you are trying to look at zeros of over a field, that will always make sense over the algebraic closure of that field. And when you come to the algebraic closure of the field, you are in this situation and you are doing variety theory, okay. So this gives you an idea how to proceed if you are having equations over a field which is not algebraically closed, okay. That is one thing. And the other thing is that many of these results that I have written down are not true if you remove the algebraic closure property, okay. That should be obvious to you because this is the algebraic closure property that gave rise to, that is needed for the Nullstellensatz. So and the Nullstellensatz is somehow indispensable in all the main statements that we are making. So if you remove algebraic closedness, that is if you take a field which is not algebraically closed, you will be in one could be in a lot of trouble. So the simple example is if you for example if you take an equation like x1 squared plus 1 equal to 0, which makes sense over the real field, that first of all the zero set is empty if you consider the affine space over the real field, because there is no zero, the zeros are they are complex roots of, so the zero set of a polynomial might become empty, okay, might turn out to be empty, and that demonstrates the failure of the Nullstellensatz if you work with the field which is not algebraically closed. The other thing is this fact that if you start with the prime ideal, then the zero set of the ideal is irreducible. That also kind of goes wrong. For example, if you take the polynomial ring in two variables over R, the reals, the field of real numbers, let us call the variables as x and y, okay. Then if you look at the polynomial xy minus 1 whose zeros are that is the locus of the rectangular hyperbola, then you can see that of course it is in two pieces, okay, it is certainly not connected, right. But the ideal generated by xy minus 1 will certainly be a prime ideal because xy minus 1 is an irreducible polynomial, okay. And you know in a unique factorization domain an irreducible polynomial, an irreducible element will always generate a prime ideal. Therefore the irreducible polynomial xy minus 1 will generate a prime ideal in R of xy, but the 0 set in A2 of R, which is R cross R, will be the rectangular hyperbola, and that is not connected, okay. So here is so the fact that the 0 set of a prime ideal is irreducible is contradicted. It is just because you are working over real numbers which is not algebraically closed. So you should always remember that when you are all these results strongly depend on the fact that the field is algebraically closed, okay. So let me write that down. Note that if K is not algebraically closed, many of the important results obtained so far may not hold. Examples is for k equal to r, real numbers, okay, x squared plus 1, ideal generated by x squared plus 1, so let me write it as in Rx is proper, but Z of this in A1R is empty, okay. Similarly xy ideal generated by xy minus 1 in Rxy is prime, but z of xy minus 1 in A2R is not connected, okay. So and if a subset is not connected, it cannot be irreducible because irreducible is very, very strong. So if the field is not algebraically closed, you will not get many of the important results here, okay. Then the third thing is to look at I mean just to look at the whole affine space. If you look at the whole affine space, then you will of course get that the whole affine space is reducible for n greater than 1, A n k is also irreducible since it corresponds to the zero ideal in polynomial ring which is prime, okay. And you know of course the zero ideal in a ring is a commutative ring with 1 is prime if and only if the ring is an integral domain, and you know that the ring of polynomials in n variables over a field is an integral domain, that is a product of two polynomials cannot be 0 without either of the polynomials being 0. You cannot have two non-constant polynomials whose product is 0, that can never happen, okay. And more generally the fact from commutative algebra is that if you have a commutative ring and you look at the polynomial ring over that commutative ring, then the if the original ring is an integral domain, then the polynomial ring in n variables over that integral domain is again an integral domain, okay. This is a fact that you can check. So more generally, instead of k, if I put any integral domain, then the polynomial ring over that will continue to be an integral domain, okay. So so this is one fact. And okay, so maybe I will continue with my discussion, and for that so I will go to what is called as Noetherian decomposition. So I will go into what is called as Noetherian decomposition. So this is another important feature of irreducible closed sets. Okay, it is in some sense it is the analog of the Noetherianness of a commutative ring, okay. So so let me make a definition. A topological space X is called Noetherian if it satisfies DCC for closed sets, okay. So DCC is abbreviation for descending chain condition, okay. And what does that mean? It means the following thing: if you have a sequence of closed subsets which is becoming smaller and smaller, okay, a descending sequence of closed sets, then that sequence has to stabilize beyond a certain stage, okay. It has, so what it means is that if you have such a sequence, then beyond a certain stage all the sets occurring in that sequence have to be the same. Another way of saying it is that if you are going to look at only strict sequences, namely a sequence in which every next set is a strictly smaller subset of the previous one, then it has to be only finite length. You cannot have an infinite length sequence like that. And actually I should tell you at the outset what is the importance of this topologically. The importance of this topologically is this gives you a handle on being able to define the dimension of a space, okay. You can define the whole notion of dimension of a space can be defined if you have this notion, okay. So so it's, if you think of linear algebra, okay, then suppose you have an n dimensional vector space, okay, then if you take a sequence of subspaces, then you see that the sequence of subspaces has to stabilize. In fact, if you take a sequence of strict subspaces, then it has to stop, because as you take a stricter subspace, the dimension falls and the dimension can't go below 0, and the 0 dimensional space will be just the 0 vector, a single point, okay, and it can't go beyond that. So if you have a vector space of dimension n and you take a sequence of strictly decreasing subspaces, then you can get only something of length n plus 1, starting with the whole space which is n dimensional, then a hyperplane which is n minus 1 dimensional, then a hyperplane in that which is n minus 2 dimensional, and you can go on up to 0. So that will give you n plus 1 terms from 0 to n, okay, and it can't be any longer than that. So so in the same way, what you are doing for a general topological space is that you are, of course in the case of vector space you have subspaces, okay, but in a general topological space what you do is you don't use subspaces but you use closed subsets, okay, and that's the difference. But the fact is that this DCC allows you to define dimension, okay. So so let me write that down. Given a sequence of closed subsets F1, or let me use Z1 containing Z2 containing Z3, okay, there exists R or there exists M greater than or equal to 1 such that Zm equal to Zm plus 1 and so on. So the sequence of a descending sequence of closed subsets at some point has to become constant, okay. Of course the other way is that if you have a strictly descending sequence of closed subsets, that has to be only finite, it cannot be infinite, okay. That's another way of saying it. So let me write that also, okay. Yeah, so I'm continuing here. Another way of saying this is that any strictly descending sequence of closed subsets has to be finite, that is given Z1 properly containing Z2 properly containing Z3 and so on, the sequence has finite length, finitely many terms. Okay, so this is another way of saying it. Okay, a strictly decreasing sequence of closed subsets has to terminate, it has to stop. Okay, and so you, of course, the main purpose of this is, I told you, is that it allows you to define dimension, okay, and but there is something more. It gives rise to what is called Noetherian decomposition. Okay, so so let me write that. Probably I'll erase this part of the board. But probably before that, let me do the following thing. Let me convince you that the affine space is Noetherian. Okay, so the affine space AN with the Zariski topology is Noetherian, and the reason is because this Noetherian condition on the affine space actually translates, if you apply the I function to the ascending chain condition on ideals of the polynomial ring, which holds because the polynomial ring is Noetherian. Okay, so that's in a jiffy saying that the affine space is Noetherian. Okay, so let me write it like this. Geometric, so there is again a geometric and there is a commutative algebraic, and the geometric thing is, so I will use the following are equivalent. Okay, for a topological space X. Number 1, X is Noetherian, okay, which is DCC for closed sets, okay. It satisfies DCC for closed sets. Number 2, but before I come to number 2, let me take the case when X is AN, okay. If you take, so I go from this picture to this picture. On this side I am writing it only for any general topological space, but I am going from here to here only when I am looking at AN, okay. And what happens is that you will see that again the following are equivalent for number 1, k x1 etc. xn satisfies ACC for ideals, okay. So this is, I mean, this is this is one of the definitions for a ring to be Noetherian. For a commutative ring to be Noetherian, ideals should satisfy the ascending chain condition, okay. And this polynomial ring is certainly Noetherian because that's because of the Hilbert basis theorem or Emmy-Noether's theorem, that if a given ring is Noetherian, then the polynomial ring in finitely many variables over that ring is also Noetherian, okay. So you see this corresponds to this, but then if you look at the definition of there are several other equivalent formulations of the definition of a Noetherian ring. Of course there is one other definition which says that if you give me any non-empty collection of ideals, it has a maximal element. So this is another condition. So any non-empty collection of ideals in K x1 etc. xn has a maximal element, okay. And usually it's a Zorn's lemma, axiom of choice kind of argument that tells you that these two are equal, right. And so you see the point is that there is something corresponding here. The corresponding thing here is, you see, ideals, if you take AN, ideals correspond to closed subsets. So the translation of that will be any non-empty collection of closed subsets has a minimal element, because you see when you take AN into the picture on the commutative algebraic side, you will take you are actually looking at k of x1 etc. xn, which is the ring of functions on AN. So ideals correspond to closed subsets, and maximal means with respect to inclusion they will correspond to minimal subsets, because this correspondence is inclusion reversing. So in fact it is true that for a general topological space also that is correct, that this condition that X satisfies DCC for closed sets is equivalent to any non-empty collection of closed sets of closed subsets. So of course here I mean closed subsets has a minimal element. Okay, any non-empty collection of closed subsets has a minimal element, and but you can write something more here, and what you can write more is, just because in this case you have a topology, the complements of closed subsets are open subsets, you can also say that any non-empty collection of open subsets has a maximal element, okay, because that is just the complement of this. Open sets are just complements of closed sets. So in fact I can also write any non-empty collection of open subsets has a maximal element. Okay, so you get that also on this side. Okay, so so it's clear that it's immediately clear from this comparison that AN is a Noetherian topological space with the Zariski topology. So I'll just draw a line here and say clearly AN is a Noetherian topological space. And you know, let me tell you again, but I'll come back to this in a later lecture, and that is, you see, the whole point about this Noetherianness is to study finite dimensional Noetherian topological spaces, and you know, by any amount of intuition, even by common sense, you should expect that the dimension of AN must be n. Okay, you should expect that, and that's what we have to prove. Okay, but for that, you know, there are two things. First of all, you should know how to define dimension. Okay, and then you have to prove that the dimension is n. Okay, and it's very easy to define what dimension is. What you do is that you imitate what you did for what you see happening for a vector space of dimension n. If you take a vector space of dimension n, if you take the longest possible strictly descending sequence, it will have n plus 1 terms, starting with the full space of n dimension and ending with the 0 subspace, which is 0 dimensional. There will be n plus 1 terms. So what you do is you define the dimension of the topological space to be, you take sequences like this, strictly descending sequences, and take their lengths and take the supremum. We have to use the word supremum because there could be, I mean, you could have larger and you could have lengths of any, I mean, you could have sequences, strictly descending sequences of any length. Okay, see, the definition of Noetherian only tells you that if you have a strictly descending sequence, it has to be a finite length, but it does not tell you that the lengths cannot exceed a certain finite quantity. So you could have sequences, different sequences, each of different finite lengths, and with the lengths increasing, being unbounded. So you take all possible sequences like this, strictly decreasing sequences, and take their length. Okay, and in fact you should take length minus 1. Okay, because you know, if you go by the vector space analogy, then the length of a strictly decreasing sequence, the largest possible strictly decreasing sequence is n plus 1 terms, and you have to take away 1 from that to get n, which is the dimension of the vector space. Okay, so that's how you define dimension, and then after you define dimension, you will have to show that dimension of AN is n. This is what you want. Okay, so what you should try to understand is that on the geometry side, you see, we have the Zariski topology, and now we are talking about dimension, which is a topological property. Okay, so you know, this is how you start studying the topology of varieties. Okay, and as I told you, this is the first step in geometry. You look at some topology, look at the topological properties, try to talk about dimension, connectedness, reducibility, and things like that. Try to understand what are the closed sets, what are the open sets, and so on and so forth. And then after you've done enough topology, then you start worrying about more complicated things, like things that are, you know, connected with analysis, like, you know, tangents, tangent spaces, and smoothness, and singularities, and things like that. Okay, which also we will do in this case. Okay, so what I am trying to say is that at this level we are still looking at the topology. Okay, and so I need to tell you also one more thing. So you might wonder how this notion of dimension is going to translate into on this direction, and the topological dimension on that side of AN being n is going to translate into what is called as a Krull dimension, okay, named after the commutative algebraist Krull of this ring, okay, and the Krull dimension of this ring is n, and that will correspond to the topological dimension of the affine space, okay. So we have to translate all this to things here, and to prove that the Krull dimension of this is n, you need some field theory and some commutative algebra, which I will recall, okay. So that is to indicate to you how this is going to go about, alright. But apart from that, what is this thing I started with? I started with this Noetherian decomposition. So if a topological space is Noetherian, the nice thing is that every non-empty closed subset has a Noetherian decomposition, okay, and that is kind of the importance of having a Noetherian topological space, okay. This break, you can break up any closed subset into a finite union of irreducible closed subsets such that no which can be made unique up to permutation of the factors in such a way that if it can be made unique if you assume that no one of these is contained in some other, okay. So it is a Noetherian decomposition that is very important. So let me write that down. That is a theorem, and we will probably look at a proof of that the next lecture. So theorem, if X is a Noetherian topological space, then any closed subset, any non-empty closed subset y of X can be written, can be decomposed as y is equal to y1 union y2 union and so on ym, and where the yi's are irreducible closed subsets, and this decomposition is unique, and the decomposition is unique up to a permutation of the sets appearing provided no yi is contained in another yj. This is the theorem on Noetherian decomposition. If you have a Noetherian topological space, you take any non-empty closed subset, you can break it down into irreducible closed subsets and finitely many of them, and you can make the decomposition unique if you assume that there are no redundancies, that is no yi is contained in some other yj, okay. And if you believe this theorem, what this will tell you immediately is that since an the affine space with the zariski topology is Noetherian, it will tell you that any closed subset of an, namely the zero set of an ideal, can be broken down into a finite union of affine varieties. Any irreducible closed subset of a, any closed subset of an which may not be irreducible, it can be broken into a finite union of irreducible closed subsets, and you know the irreducible closed subsets are called the affine varieties, and therefore you get a decomposition of any closed subset into finitely many affine varieties, and those finitely many affine varieties are called the irreducible components. It is just like in topology when you have a space which is not connected, you know, you can break the space down into union of its connected components. Okay, in the same way what you can do here is that any subset of a Noetherian topological space, any closed subset of a Noetherian topological space can be broken down into irreducible components, and these irreducible components are closed. So these yi's are called the irreducible components of Y. Okay, then the yi's are called the irreducible components of Y. Okay, so I'll end with this, and I'll just make a final remark to tell you that you see the notion of Noetherianness is essentially needed on one hand to make sense of dimension, okay, and on the other hand it is very helpful because it allows you to break down any closed set into irreducible closed sets in a nice way, okay, and that for us is important, and all this for us is important is because you can talk about dimensions of affine varieties, okay, and you can also break down any closed subset of affine space into its irreducible components, which will be affine varieties and which will be essentially unique. Okay, so that is the importance of the Noetherianness, and so this is the geometric part of it. But if you come to the commutative algebraic part of it, what is it? It is just the usual Noetherianness of the polynomial ring. So you see this is the beauty of algebraic geometry, that some nice property on one side gives rise to properties on the other side which have nice consequences. So after all, the fact that the polynomial ring is Noetherian, okay, is a completely commutative algebraic property, but when you translate it to geometry, you see the advantage is that it allows you to define dimension, okay, and we are eventually going to prove that the dimension of an is n, as you would expect, okay, and it also allows you to decompose any closed subset into affine varieties. Okay, so you see this is how a nice commutative algebraic property translates into such nice things in geometry. Okay, see this is essentially the attraction of algebraic geometry, to take something on one side and try to go and investigate what it means on the other side. You get interesting things on the other side, and here we are going from the commutative algebra side to the algebraic geometry side. Okay, so I'll stop here.